Welcome to what is the last video in the Ultra-Scale Playbook series. So I guessed it would take around like 10 to 12 episodes. When I began, it took around 16, so classic planning bias. However, it would have taken even more had I done this section. So starting from memory coalescing to fuse kernels, which are, I guess, somewhere here, fuse kernels, and then flash attention. I was trying earnestly to understand these topics so that I could present it to you, but I just didn't have enough understanding, so I didn't want to give you guys like a half-ass presentation of these concepts. There are better resources, i.e. Simon Boehm, for example, of anything to do with CUDA, just read his resources. And also Elliot Ulrich has a really good CUDA course, which I'll link below. So I just wanted to jump straight into mixed precision training instead, which is the last topic in this playbook, and one which I have quite a lot of knowledge on, so I'm happy to talk about it. And let's start. In various sections on this book, we talked about lower precision formats and their impact on the memory requirements for storing activations, parameters, and optimizer states. And now we're going to dive deeper into the details of these formats. MPT, or mixed precision training, as the name suggests, involves mixing different precision formats when training. And the default numerical precision of PyTorch tensors is single precision floating point format, or FP32. So it's a 32-bit format, which is 4 bytes. So 4 bytes of 8 bits, 4 times 8 equals 32. And I think this is what they just said here, where we have a sign bit that determines the number of positive or negative as the first bit, the mantissa, which determines the significant figures of a number, so like what are the actual digits, and then the exponent, which controls the magnitude. So the exponent controls the dynamic range, and then we have the mantissa, which controls like the precision of the number. And then the principle of floating point numbers can be seen as well by looking at scientific notation, such as negative, which would be the sign bit, 5.734, which would be the mantissa, times 10 to the power of 7, which would be the exponent. So here we also have the different popular formats. So although float 32 is default in PyTorch, there's these other ones. And one thing that I learned when going through this is that you may wonder where bfloat 16, which is the most popular half precision format, comes from, like the B, and it's actually from Brain. So Google Brain made this format, and they just added B to the beginning of the format name. So we have some popular formats here: float 16, bfloat 16, and then float 8 and float 8 with different exponent and mantissa allotments. And you'll notice that these two formats, as well as these two, are like conjugate pairs, which is to say that one focuses on the dynamic range, which is the exponent, and the other focuses more on precision, which is the mantissa. And I'm going to explain this with these very well done diagrams. So reducing the total number of bits comes at no price, no free lunch here, but we have some control over how to pay. Either we sacrifice more bits on the mantissa or exponent. For this reason, there are 2 float 8 formats and 2 float 16 formats. So we have the dynamic range here, which for float 32 and bfloat 16, the purple and the turquoise, so I'm not sure what color that is, one is from 10 to the negative 40 to 10 to the 40. So that is quite a large dynamic range, 80 orders of magnitude, and float 16 sacrifices a lot of range while bfloat 16 maintains the full range. The 2 float 8 formats reduce the range even further, where E5, E2 can maintain float 16 range because it has the same exponent as float 16, and E4, M3, which is this one, has an even smaller range. So how come some formats are able to maintain the range and others not? And let's investigate this by looking at the other side of the trade-off, which is the precision, precisely plotting 10,000 points between 1 and 2. So this graph is split up into 10,000, I guess, lines. So each of these lines is like 1/10,000th of the range 1 to 2. And yeah, each point is rounded to the nearest representable number because there's only 10,000 points, and there are an infinite number of numbers within the range 1 to 2. We can see here that bfloat 16 maintained the range of float 32 above, but did this with the cost of sacrificing more precision. So if we look at float 16 and float 32, they have the same amount of precision. It's just that because of the different exponent for float 32, it's essentially scaled to a larger extent. And then in the case of float 2, the situation is even more dire, as E4, M3, which is the orange one, can represent 7 numbers between 1 and 2, and E5, M2 can only represent 3 numbers on the interval 1 to 2. So it's pretty impressive. And just for information, we have 1 plus up to 10 to the power of 0, which is 1. So we have, for example, this number here would be 1.1. So 1 plus 10 to the negative 1 is 1.1. That's all there is to it. And a common metric, therefore, to measure format resolution is epsilon, which is the first representable number after 1, which is to say the line closest to the left. For float 32, the format is 10 to the negative 4, which is to say like the closest number that can be represented is 10 to the negative 4. Apparently it's actually 1.19 to the power of negative 7, but I assume this is just because of the rounding that they did, that it turns out to round down to 10 to the negative 4, but if somebody knows specifically why they have this discrepancy, let me know. And then for float 16, the epsilon, which is the closest number once again, after 1 is 1 plus 10 to the negative 3, which would be 1.001, if I'm not mistaken. And if we look at B float 16, which is the purple one, it's not more than, but it's almost an order of magnitude less precise. So near 1.01, which is 1 plus 10 to the negative 2. The idea of mixed precision training is to use some of these lower precision formats while maintaining the performance of full precision training. And this means that we're going to have to keep some things in float 32. We can't totally abandon it. And we'll usually need to maintain, some ports in full precision. This is why it's called mixed precision. So let's look at how models can be trained with 16 bits and then even 8 bits. So when it comes to 2 byte training, naively switching all the tensor and operations to float 16 doesn't work, and the result is usually diverging losses. However, the original MTP paper came up with these 3 tricks to match float 32 training stability. The first one is a floating point 32 copy of weights. So there are 2 possible issues with float 16 weights. During training, some of the weights can become very small and will be rounded to 0. However, even if the weights themselves are not close to 0, if the updates are very small, the difference in magnitude can cause the weights to underflow during the addition. Once the weights are 0, they will remain 0 for the rest of the training as there is no gradient signal coming through anymore. And regarding the second point about the weight updates underflowing, I have this explanation courtesy of Claude, which I'd like to present because I didn't get the intuition. Let's see. If the weight is 0.5, but the gradient update is 1 divided by 10 to the power of 6, floating point 16 can't represent the difference between 0.5 and 0.500001. And this is exactly coming back to the idea of epsilon, which we discussed, because the next number, which can be represented by FP16, I believe was 1.001. So we're having precision in the tenths, hundredths, the thousandths place, but we need it to be in the 10,000, thousand, in the millionth place of the decimal point. So the addition gets rounded back to 0.5, which means that no actual update happens. We're not actually learning. And this is magnitude-based underflow. The update is too small relative to the weight's magnitude to be representable in floating point 16's limited precision, even though neither value is close to 0 individually, which is to say that we can still add this number if we were able to represent it within the floating point 16 framework, but it's not possible due to the underflow, which is a result of the lack of precision within this data format. And moving on, we have loss scaling, which is a similar issue regarding gradients, as they tend to be much smaller than 1 and then are also at a risk of underflow. But a simple yet effective strategy is to scale the loss before the backward pass and unscale the gradients after the backward pass. This ensures that there is no underflow during the backward pass, and the scaling is not affecting turning as we unscale before processing the gradients further, which can be done by clipping and the optimization step. So unscale before processing the gradients, which is to say during the optimization step. And when we talk about scaling, so this means that once we have our error, then we will just scale it up by some factor. I'm not sure what the state of the art or like best practice is. And then once we have our updates, of course, the gradients will kind of be inflated, but at least then we'll have the signal that was passed through instead of having this instance where we have 0.001 that's rounded down to 0. And then we'll scale everything down and also clip. So I suppose if there was one scaling incident where it just scales it quite a lot and then it becomes like an outlier, then you would just define a range where you would clip the values between so that there are no like outliers that are a result of the scaling. And then thirdly, we have accumulation. So when performing certain arithmetic operations in 2-byte precision, such as averages or sums, we also face under overflow issues, and this is why we do gradient accumulation in floating point 32 precision. and therefore the solution is to do this, and then only cast the final result back to 16 precision once we have accumulated all the gradients. Because if you think about it, during the gradient accumulation step, if we're doing it in 4-byte precision, then we're maintaining a lot more information, and then there's much less rounding error, such that when we round it back, we'll have a more reliable number, which is to say, instead of rounding every single time we add it, we're only rounding once at the end, so there'll be much less rounding error. With these techniques, we can get a stable training while benefiting from a higher throughput due to the faster, lower precision arithmetic operations. And now we're going to ask, can we go to 1-byte floating point training? And even if we perfectly overlap communication with computation, we always eventually run into the low-level theoretical flop limit of hardware itself, which is to say the efficiency of each individual operation on our hardware. And this is where numerical precision is very important. For instance, on an H100 GPU, FP8 gem operations, which is general matrix multiplication, are twice as fast as the theoretical floating point operations per second of bfloat16, making lower precision training on an attractive path for further optimization. Which is to say, like, even if we had the theoretically fastest floating point operations per second on bfloat16, it would still be twice as slow as what we can get with FP8 practically. And recent research has demonstrated the potential of FP8 training for large language models. However, FP8 training still introduces a significant challenge, which is stability, because at lower precision, numerical instability often leads to loss divergence, making it difficult to match the accuracy of higher precision training. And of course, as you increase learning rates for a fixed model size, then instability will also change because you're making the updates larger, and if there is an incorrect gradient in the loss landscape, not an incorrect gradient, but perhaps a gradient which locally is optimizing it but not globally, then you can get a divergent loss curve, which once again makes FP8 pre-training particularly tricky. And in this example, we have naive FP8 training, which I assume is just like putting everything in a 1-byte representation, which is just not a good idea. Then you have the Nanotron early FP8 training prototype here, and then you have bfloat16 as a baseline, which you can see is very stable, or if you look at this curve, at least to me, it looks very stable. So when we talk about 1-byte training, the first very successful training run that was published was DeepSeek v3, where the authors carefully analyzed each operation of the forward pass, which is represented here as fprop, as well as the activation, which is here dgrad, and the wait backward pass, which is wgrad. Similar to BF16 mixed precision training, some aggregation and master weights are kept in high precision, while the operations themselves are performed in FP8. So in this diagram, you can see that we are converting in many sections to different types of data formats, FP8, of course, being the most memory efficient format. And then the only time that we convert to 4-byte precision is the master weight for gradient accumulation, which once again is FP32. And in order to switch from higher precision to lower precision with smaller range, because of course FP32 can represent a much wider and more precise value range than, for example, FP8, we need to normalize the range of activation values, for instance, by computing their absolute maximum, which is to say, like, we're not just going to directly compute or translate the number 10 in FP32 to 10 in FP8. Instead, we'll take the range and then we'll subtract by maximum value and then divide by the absolute range. And then this will give us a normalized value, which will then be converted into the given data format. And DeepSeek v3 specifically introduced a specific quantization scheme where the ranges are normalized per tile, which is to say, like, per tile of the matrix, so like a specific row or column, which is to say 1 by 128 for input/activations and 128 by 128 for weights and scale elements. So what is this doing that wasn't done before? Before, it was done globally. We would take all of the values in a specific weight matrix and then get the minimum and the maximum to be our range. But the thing is, if one outlier was like really big or really small, then it would completely skew the normalization range. So instead, we're taking a smaller tile, which is 1 by 28 for inputs and activations and 128 by 128 for weights and scale elements, such that it's more localized. And this can be done or thought of in a similar token for photo normalization in terms of lighting. If you do it on a global scale and there's like a really bright spot on the picture, then like the sun, for example, then that will screw up the brightness normalization across the image. But if it's done tile-wise, similar to like convolution kernels, then it'll be more localized and better precision and less essentially effect from outliers. So this is the analogy which I like to think of when we're talking about this more local normalization. And then, it's less strongly impacted by outlier values and activations, like, for example, the sun in a picture of a landscape. And there's a number of additional tricks they proposed. So if you would like to, go check out section 3.3 of the DeepSeek v3 technical report. And in fact, here we have the summary of known FP8 training approaches with the amount of memory reduction achieved from the standard bfloat 16 with FP32 mixed precision baseline, which takes 20 bytes per, parameter. So we have to take into account the gradients, the model weights, optimizer state, as well as the master weights. So apparently the Nanotron FP8 format is the most optimized. Oh no, I didn't see the LM03 level where we have only 9 bytes stored, but you definitely take a big sacrifice in performance for this. So if they could make this stable, then I really commend them, because that's a larger than 50% memory optimization. And overall, FP8 remains an experimental technique and methods are still evolving. This was written in February to March, and now we're in June. I'm not sure to what extent this has changed it, but maybe it has. And given its obvious benefits, however, it will likely become the standard and soon replace BF16 mixed precision, even so much more so because of the hardware, which is now becoming available, such as Blackwell. I guess it's written here to handle these operations specifically, and even Blackwell has announced support for FP4 training, or not has announced, but has support, which will further speed up training, but without a doubt also introduce training stability challenges. This last section concluded our journey in the land of fast and large model training on tens of thousands of GPUs. Now we're going to slowly turn off our GPU cluster and get to the conclusion. So congratulations, we started from understanding how to train a simple model on a single GPU all the way to mastering all the intricate techniques used to efficiently train massive LLMs like Llama 405B and DeepSeek v3 on thousands of GPUs. And by now you can read a diagram like Llama's 340 parallel setup with relative ease. So to get an idea of what is happening in this diagram, we have 4 dimensions of parallelism. We have pipeline parallelism, context parallelism along the sequence length, tensor parallelism along the head dimension or the hidden dimension. And then we have data parallelism, which would be along the data side, the batches, which is in this case FSDP, fully sharded data parallelism, which is the same thing as the zero redundancy optimizer 3. And let's read the figure description to understand what's going on. GPUs are divided into parallelism groups in the order of tensor parallelism, context parallelism, pipeline parallelism, and data parallelism, where DP is FSDP. In this example, 16 GPUs are configured with a group size of 2 per parallelism scheme. And a GPU's position in 4D parallelism is represented as a vector D1, D2, D3, D4, where this is the index of the ith parallel dimension. This means that we have a 8-head multi-attention setup because we have 8 GPUs with TPU 0, which means that the attention head is split up into 8 heads, or the multi-attention head is split up into 8 heads. And then on the context parallelism dimension, we also have the sequence length split up into 8 GPUs. In this case, we're sharding the sequence length along this dimension. And then when it comes to pipeline parallelism, we have it layer-wise. So this is the first layer, PP0, and then this would be the second layer of the model. And then when it comes to data parallelism, we have it such that this entire batch would handle one mini batch, and then this right side will handle another mini batch, since we have DP1 on the right and DP0 on the left. Orchestrating large clusters of GPUs to train LLMs efficiently is no easy feat, but through this series we learned how to optimize computations and communications between GPUs such that they run with maximum utilization as much as possible, and this involves choosing the right parallelization strategy for a given model and cluster size, overlapping communication and computation where possible, and writing custom kernels that take into account the hardware layout to perform an operation as fast as possible. But I'm not gonna lie, we did skip that. You might still believe that this knowledge is niche and esoteric, but both the AI builder community and model sizes are growing rapidly, which means that the community of people using distributed techniques for inference, fine-tuning, and training is increasing exponentially, as well as making distributed training setups more and more common. Diving deeper into all things distributed might thus prove very timely. At least this is my thought. And this has been a long journey, but not just for you. They've ran thousands of benchmarks on a GPU cluster, and now they're going to talk about what's next. So if you want to go beyond this, because right now we only have a overview of the main distributed techniques, but we have not really gone deep into the subjects of the individual topics. Then some things you can do are to carefully read landmark or very recent papers, and there's an extensive list of this in the references, which is just in the bottom of the paper. There's another typo here. Start from scratch and implement an algorithm yourself. This is the most effective way, which I don't do enough, but often a method only fully clicks if you implement it yourself. Thirdly, you can dive into one of the widely used frameworks and start contributing by fixing bugs, answering issues, or implementing a new feature. This is a really good way to get into ML fields. For example, you can just contribute to the Hugging Face Transformers GitHub repository, for example. And yeah, they hope that this book was helpful. One thing worth noting is that they are making a physical copy of the book. So if you're one of the first 50 people, I'm not sure if this has already been exhausted, probably it has, then you can fill out this Google form and perhaps you'll get a physical copy in the mail. So that was all for the Ultra-Scale Playbook series. I hope it was worthwhile, and thank you for watching.